moment generation function, when you put t inside of it, it just outputs the expected value of e power of tx. Yeah, so that's the moment generating function. You can see that this is a function of c, right? So we want to see all moments of x, such that takkan hilang, kau takkan hilang. All moments of x such that x is all moments of x such that x is identically distributed to the exponential and the variable of dimension lambda. So since we know this guy, we can do this directly. This would very soon. It's not that difficult. It's just when you take the t to 0 and take the kth derivative. It's not anything special. So this would be expected value. This. Takkan hilang. And then this is if you write in integral form. Actually, jalan nggak ya slide-nya? Okay. Actually, if you write it in integral form, this thing becomes I think it is this thing. And this guy is just, you take out the lambda and this becomes t minus lambda x dx, and you know that this guy is just 1. No, it's not 1, but it is 1 over t minus lambda, so this should be this guy. So we know that, and we consider taking the derivatives over t. So let's see what I don't know why you care about taking the derivatives. This is just something that's written in the notes. So if you take the first derivative of this guy, then what you get is it is on t, so it's minus 1 times lambda over t minus lambda squared minus m, and then you take the derivative again, then you get minus 1 minus 2 times lambda over t minus lambda power of 3. Right? Actually, do you even need this? Oh, this is supposed. Okay, I think I did something wrong. Lambda minus t. There must be some mistake over here. Oh, it should be the negative of. So this should be lambda minus t. And so this guy doesn't exist. The negative should not appear. So you can tell that if you take the kth derivative of t, of the moment generating function of t, it will just become the k factorial times lambda over t minus lambda power of k. So you see that this is very this is very similar to the Poisson, right? The kth derivative is very similar to the Poisson random variable. Not quite the same though. So if you take the moments, oh yeah, okay, I see. Yeah. So this is where the formula is used. This guy, you can prove that you can prove very easily that this is equal to m. You take the kth derivative, right? You give the value 0 over there. So plugging this here, we get k factorial. Am I doing this right? Should be correct. This is it's supposed to be a +1. So k factorial times lambda over minus lambda. This is lambda minus t. I have to change this part a bit. It's t. Lambda minus t. Lambda minus t. This is lambda over k plus 1. Then you get k factorial over lambda power of k. Easy stuff. The rest of this is computational. It's not very interesting. So we will move on to Markov and the Chebyshev's inequality. So, yeah, start off with Markov. So, what is the point of this though? This guy, probability greater is less than or equal to expected value of x divided by a. This is quite easy to show. Because if you look at this guy, right, equivalently this, I kind of forgot the proof. I know like roughly the intuition behind the proof. Because if you write this thing, this is minus until a to infinity, and this is f of a times, this is wait, f x and x dx. Same thing. So maybe we add that x is non-negative. So if x is non-negative, this guy is positive, and you look at this guy. If you replace each of x here with a, then you would get exactly this thing. So now we try to show the Chebyshev inequality. It says that, I recall that there is one more. So we will end with the weak law of large numbers later. So Chebyshev's inequality, it says that given, so proof of before, you change each x with a, you will see that when you do that, the value of that integral decreases. Chebyshev's inequality says that given x has equals mu, and var variance of x equals this thing. Then we want to show that the probability that is greater than a is less than or equal to variance x over a squared. What the ya udah, nggak apa-apa. And so we see if there is usually what you do for this. You see that both numbers below have an a square. So if you just square this thing, then you get the variance. Then it's exactly so. To be more elaborate, use when you square this quantity, it's equivalent, right? So using the Markov's inequality, remembering that this is the variance, and you take that, literally that. This is, if you take the expectation of that guy, then you get the variance, so you get this inequality. Very quick stuff. So what is the point of doing this? If x has finite higher moments, then we can get better bounds and tail probability. Yes. Because, in a sense, so the point of this is, we will try to see. Taking the power of p. Yes. So basically, if you power it many times, so let's see. Okay, let's see if there is some application here. E of tx. For t inside of this thing. This guy, you just probability of x. Wait, I don't know where this is coming from. Don't know where this is coming from. Should it doesn't look like this. Perhaps if you take the power, probability that e power of x t is greater than e power of ta. Yeah, it's just pretty much the same. You just change the x greater than a into this, and then plug in the Markov inequality again. But what does this thing entail though? So So now we try to prove something that I feel a bit fuzzy, which is the weak law of large numbers. So, this is a theorem of the weak law of large numbers. Let's say we have some random variables such that this, and define as n as 1 over n, where until n of xi. Okay? Then for any, I should mention that this thing xn for this guy, for any exponentials is IID RV. And for any, so for any greater than 0, we have the probability of Sn minus mu greater than epsilon approaches 0 as n goes to infinity. Alright. This is just saying that as n minus, no, this is just saying that if you draw the distribution function, right, and you have this point mu over here, we should describe the mean like we have something like this, you know. The value will be trapped inside of this guy. Now, okay, so we'll see what we can do about this. Maybe I should try to think about it for a bit. It's a good exercise. You know, by the way, I was thinking about this problem. It was quite interesting. I'll write it down at the bottom here. So, this is a very famous property about the longest increasing subsequence. It's very, very computer science thing. So, if you have, before I continue to this, I just want to discuss something that I've been looking at for quite a bit. Regarding longest increasing subsequence. So the longest increasing subsequence is defined as if you have some sequence of integers, not necessarily integers, but numbers, a1 until n, and you say you have some permutation of this, and then you say what is a longest increasing subsequence. It's just like if you take ai1 until aik, right? Such that ai1 is less than ai2 until aik, and i1 is less than i2 and so on until ik. So this is an example of an increasing subsequence, right? And then we want to take the longest one. The question is, how would you describe the size? How would you describe, on average, the size of the LIS. So you denote that with expected value of LIS. And there is a very neat theorem by Paul Erdős. It's called the Erdős-Zecharius theorem, which I just knew this. I actually just learned this very recently. I mean, I didn't learn it. I just came to know about it very recently. As taught by, it was a friend of mine told me about this theorem, and apparently it's by the statement of it. It's a very Olympiad-esque theorem. It's basically, it says that if you have the longest possible subsequence, it's like if you have A and B, then, how do I say this? I only know one direction of it. So like if you have something that's around this size, right, something around this size, a sequence of integers of this size, then you have either LES of size A or a longest decreasing subsequence of size B. Longest decreasing subsequence is basically just LIS and you reverse it, you know. Yeah, so this is very neat, particularly for this guy, because then you could just hit this number. You could just try to guess that if this is n, then you would think that this is probably somewhere around square root of n. This is also somewhere around square root of n, right? And it's actually, this guess is correct. So this guy is around square root of n. There's a way for you to see it this way. Now there are many proofs. There was one very disgusting, not disgusting, but very, computational proof that required a lot of approximation. The Stirling approximation, which I don't really remember, but it had something to do with fixing the permutations, fixing certain part of the permutations given some random permutation. So like if it takes some I1 until Ik, what is the probability that this guy is sorted, right? Because the probability that this guy is sorted can give you some upper bound to the event that you have an LIS. So that was a rough idea for this thing. I won't go into the nitty-gritty details about the approximation because I forgot about how to do that. Now, apparently there is extended version which by the sound of it may seem more deterministic, by the sound of the problem would seem more deterministic, as in like there's actually something that you need to find. And it's this question: if you have an n by n matrix, right, of integers, or of pairwise distinct integers, or numbers for your liking, then there exists a permutation of rows such that there does not exist a column, okay, or maximum LIS of any column. So let's say that just is C is inside of O square root of n. So there is such a permutation. And in fact, this will be actually 2 times square root of n. This is quite spectacular, What I like to do for this sort of problem, I mean I didn't solve it, but what I like to do is consider the case where you have just an n by 1 matrix. And it becomes, so much easier, because then you just make a decreasing subsequence, right? if you have like 5, 4, 3, 2, 1, then there's, you know, all the numbers are decreasing, going down. So you get what I'm trying to say. Now consider the case that you have an n by 2 matrix. Alright. If you have an n by 2 matrix, then the worst case is that if you have, okay, not the worst case, but one case, one sort of like construction that would make, that could possibly make you doubt this, is if you have this guy, n unto n, right? If you have such a thing, right, then by the Erdo-Sepers theorem, you know that either going down there is a square root of n, like either way, because they are opposites of each other. If you try to minimize this from one side, you are maximizing it from the other side. Right? If you try to minimize the LIS going down, then you are sort of like, if you're minimizing the LIS from this guy, then you are maximizing the LDS, which means you are, what? Maximizing the LIS on the other column. So with this, then any permutation will yield a maximum LIS of at least square root of n. So that's not good. That's why what I did for this was just simply duplicate, assuming that we know that the expected value, right, of some LIS is around square root of n, which you can, I mean, left hand side you can write that as like probability of x equals k times k, and you summate that, right? Now, if you change the question into expected value of the maximum LIS between the two, then you just need to consider that you can sort of like multiply this by 2. I'll leave that to your, I'll leave that as an exercise. But either way, then you get some, you know, like some approximation to square root of n, which is quite good. But you can't extend this solution to an n by n matrix, because then you'll be multiplying a permutation by n, and this becomes n square root of n, right? It's so much larger. But the main problem with this is the left hand side does not at all properly describe the probability distribution of k. That's the main issue. Even with just n equals, even with just this guy being 2, right? The number of columns being 2, right? This thing doesn't make sense, because when you group these two together, then the total probability will become 2. That shouldn't be possible. So this, like, very this stupid, not stupid, but this idea doesn't really, you know, help us much, because it doesn't describe the probability distribution. Of course, we want the probability distribution to be something like this, right? So that the weights on k is very small as k gets larger. So there you go. So this is one problem I've been thinking about for quite a while. I've been thinking about this problem for quite a while, and I think the solution, I don't know the solution yet. I think most likely I will read the solution, because it uses a lot of like approximation, which I'm not very familiar with. But back to the point, now we continue to work with the weak law of the large numbers. I mean, with the Markov, I don't see a point of doing this. I mean, what we do know about So, okay, what is this supposed to be? We feel like powered it. I mean, since we just learned moment generative function, we might as well try to make use of it for any epsilon. What was it again? This guy is supposed to be bounded by variance, right? Of Sm. I think the variance should get smaller. The average will stay, but the variance will. I would assume that it gets smaller. Okay. This thing should be below its epsilon square. Maybe we look at this guy. What is the limit as n goes to infinity of the variance of Sn? Well, you know the definition of a variance. It's just the expected value. I mean, there's many ways to write it, but we'll write it this way for now. Mu n square that. What is it supposed to do? It's supposed to be Sn. Right. Okay. Actually, no. I think it would serve us better to use this definition, Sn square minus Sn square. So perhaps it would serve us better doing this with this. What is this guy supposed to be? Sn square